Marvin, hello. Alex, what's going on? Sorry for keeping people waiting.
Hello, hello.
Hello, Alex. Nice to see you. Nice to see you, Herman. Nice to see your screen, at least.
Hey.
Oh, and Toru's here.
Yeah.
Full house. I need to make it so you guys can like get in the Zoom room before I can. That's how it was. That's how my meeting used to be, and then they updated Zoom, and now it's not. But the point is like I mean, you guys don't need me to hang out. I don't need to be the nucleus of your group. You guys should be able to do things outside of me in my Zoom room. For serious, also I feel like whenever a Zoom room starts, everyone has to stream in like one at a time. Or it'd be better if you guys were already here. Hello, Afra. How's it going?
I'm good. How are you?
I'm good. Thanks for asking. So 5 people, including the teacher. That's a class right there. That's enough for a start. Does anyone have any questions or anything like that before we begin?
I have questions about the test one or exam one. Oh, it was weird. I thought I would do worse, but it came out better. But I'm still not happy with the score. It's just a weird feeling.
Yeah. I think that's because we're at the stage right now of discrete math where we kind of get it. It's like we get it enough by we. I mean, not me. I'm solid, but I'm saying the class. I think as a class we're starting to get it, right? But it's kind of like we don't necessarily get it enough to know we're right, which is it's an interesting in between stage to be. Where it's like you are right, but you don't know you're right. It's kind of like if you don't know you're right, that feels like you're a little less right, even though you see what I'm saying? I don't know. But as we do more, and as we keep going more, it'll still actually, the weird thing is, the more we move ahead, the more we'll solidify things.
Is it gonna get harder ahead when we move?
No. It doesn't really get harder. It's just kind of different. In fact, now that we're in this proofs, now that we're in like the area of proofs and everything like that, we're kind of gonna leave behind. We're kind of gonna leave behind almost everything we've done, but not really. Like in the sense that we're not gonna see truth tables anymore. We're not really gonna see logical equivalences anymore. But they're all still happening under the hood, right? Like we're still gonna have. Like for all, like for example, like the universal statement, like for all x and d, p of x and q of x implies like r of x or something like that. Like the point is that we have our statements. We're still gonna have ands, and we're still gonna have conditionals, and we're still gonna have all of that. So there's still all that happening under the hood, and then the argument forms are still kind of happening under the hood because we're still gonna break things into cases. And we're still going to use kind of modus ponens and contrapositive modus tollens. We're still going to do all of that. We're still not really going to talk about it. So it's all going to be there, but it's all moving on. It's all going to be different things. Like now the hard parts are going to be different things. So it's not any harder, just different. And I think more fun, personally. This is why I'm not a logician, but a mathematician. Because all the stuff we've done so far has been logic. Now we're getting into math. As soon as we introduced the natural numbers, that's when math started. And where does it end? No one knows. But the point is, it's not about the destination, it's about the journey. So if anyone has any more questions, that's your cue for questions. Then let's get started. Perfect. So let's get back to section 4.2. Section 4.3 is kind of where we're hanging out now. Chapter 4 really all blends together nicely. But we're talking about divisibility stuff, and we have a proof to finish. Before we finish that proof, I kind of want to talk about divisibility some more, just because I realize this might be a new concept to some people. I mean, we probably have seen it. We've seen multiples and greatest common divisors and stuff like that before. Divisibility. But, it's been a while ago, and now we're talking about a much more rigorous context. So let's get going with this divisibility. So let's recall, right? Like what divisibility even means. So recall, or at least for integers, divisibility only makes sense with the integers. Oops. Recall for any integers a and b, a divided by b, what that means is a is a divisor of b. So I'll say a divides b, it's like a verb. A is a divisor of b. B is divisible by a. B is a multiple of a. All those things, they all get to the same thing, and that is that there's some integer, k such that b equals ak. Right? That's what it means to divide. Real simple. We've seen it before. And so being even just means that you're divisible by 2. It means that a number being even means 2 divides it. Right? That's by definition. And kind of maybe the reason, well, yeah. But kind of a way to extend the idea of even, maybe, if you think about it, right? Even means you can be an even number can be divided by 2. We also have numbers that can be divided by 3, numbers that can be divided by 4. And these are all kind of similar concepts. So, for example, actually first, let's write this formally. Formally, what this means is that for all a and z, and for all b and z, we say a divides b if and only if, it goes both ways, if and only if there exists a k such that b equals ak. And remember, when we first brought up biconditionals, we had things like, you're like like a person's bald if and only if they have no hair. And we're like, yeah, biconditionals are kind of like definitions. Well, this is a definition, right? Like biconditionals really come up when you're just talking about rewriting things. So a divided by b, it just means this. Because whenever a divides b, this happens. Whenever this happens, a divides b. You guys know what I'm talking about. So this is how you write it formally. This is what the concept of division is. So, for example, right, 15 divides 45. Why is 15 divide 45? Because 15 times 3 equals 45. The point is, 45 is an integer multiple of 3, or of 15. You can multiply 15 by an integer, in this case 3, and you get 45. So that's why 15 is a multiple of 45. That's why 45 is a multiple of 15. That's why 15 divides 45. Okay, to keep all these things straight just for another hour. Okay. And this also tells us, by the way, that 3 divides 45. Right? So that's interesting. Yeah. So another example would be, let's say, 2 divides 10. And 2 divides 10 because 5 times 2 equals 10. Meaning 10 is the integer multiple of 2, because 2 times the integer 5 is 10. And so, like a way you can visualize that maybe is that if you start with 10, if you start with 10, right, you can break it up into groups of 2. That's what it means for 2 to divide 10. For 2 to divide 10, it means that you can break 10 up into these groups of 2. There's nothing left over. You can evenly divide it into groups of 2, right? We could do the same thing with 45. We could have drawn 3 15s, evenly dividing 45 into 15s. So that's what it means to be a divisor. Yeah, that's all I want to say. So, let's do a proof with this. A simpler proof. And I'll call this the transitivity of divisibility theorem. And this is real simple. Oh, it makes sense. It might look weird. And that is, well, I'll just write I'll just write it first. It means divisibility is transitive. It's one way to say it, but we haven't really defined what transitive means in this class yet. What transitive means for any kind of operation is that, like, for example, if A equals B and B equals C, that means that A equals C. Something like that, right? Or like if A is less than B and B is less than C, then A is less than C. Now, the reason this works is because equals and the less than sign are transitive, but not everything is transitive. It's kind of hard to think of one on the top of my head because most things that we do, most things that, without using too advanced math, most things kind of end up being transitive, but it's not obvious that everything's transitive. Yeah. If you want a really complicated example, I can give you one after class. But anyway, so divisibility is transitive. What this means is, i.e., for any 3 integers, A, B, and C, if A divides B and B divides C, then A divides C. Right? This, I think, should kind of make sense. And like for example, let's do an example. For example, we could say that, yeah. For example, 3 divides 12 since 4 times 3 equals 12. And 12 divides 24 since 2 times 12 equals 24, right? And 4 and 2 notably are integers. That's why this is division. Or that's why they are divisible. So yeah, so 3 divides 12 and 12 divides 24. And so now we can draw that, right? We can draw so this is a drawing that shows that 3 divides 12, because this says 12. So you can say that 3 divides 12, right? Because we can split it up into 4 pieces, each of length 3, right? 3 evenly goes into 12. We can also see that One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22. Thanks, 24. We can also see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. So we can see that 24 is divisible into 2 pieces of length 12. And then because we know that 3 divides 12, we can break each of these pieces of 12 into pieces of 3. Right, the point being that clearly, right, if 3 divides 12 and 12 divides 24, then we can figure out how to break 20. So we figure out how to break 24 into pieces of 3, right? Benay asked, are we saying divides as being explicitly just a percent? Oh, mod b equals 0. Yes, Benay, that'd be what you think about it. Exactly. And it's going to come up. We have mods coming up in a few weeks. So good job. But yeah, so I think clearly this transcendental thing makes sense, because if A divides B and B divides C, well then just think about how B goes into C and then put A into each of those B's, and then you have it. In this exact example here, right, the way you mathematically do it is we have 4 times 3 equals 12, and 2 times 12 equals 24. So then 24 equals 2 times 12. And then 12 equals 4 times 3. This whole thing equals 2 times 4 times 3, which is 8 times 3. And 8's an integer, so 24 is an integer multiple of 3. All right, we're going nice and slow, I hope. So we're all getting it. The slow dance of divisibility. So yeah. So now I think we have enough information. Let's just write this formally and do a proof. So the formal way to say this is for all A and Z, and for all B and Z, and for all C and Z, A divides B and B divides C implies A divides C. Here's a question. Do I want an arrow going this way?
No. You do not.
No. What was that, Alex?
Well, you can actually just think about it with just one thing, right? If B divides C, C doesn't necessarily divide B, right? It's too big. It could be, for example.
Yeah, exactly. I mean, we might not even know that there is a B possible, in the sense that, like, we know if this happens, this will happen. That's why the arrow goes this way. That's what we're going to prove in a second. But if you have A divides C, for example, if you have, like, well, I guess it depends how you look at it. But anyway, we're just going to go one arrow for now, because going backwards, like, what even is B? Like, if you have A divides C, well, what even is B? I guess if there was a particular B that would have this happen, then it would work, but then it would have it happen. It's kind of circular. The point is we only want to go one arrow. in this case. So, let's prove it. Proof. Okie dokie. So to prove this, right, is a proof by direct method because we're proving something about infinitely many things. We're proving something about all possible A, B's, and C's which make this work out. So this is a very big set of things. Method of exhaustion won't work. We're using direct proof. And what's the start to all of our direct proofs? We always say let. Well, what do we start out with, right? I mean, like we have to start from somewhere. We have to start from something. We need something to play with, something to work with. So what do we start with?
A divides B and B divides C.
Yeah. So this is a universal statement, because we have the for alls here, about a conditional. And the way that you prove a universal conditional is so the way you prove a universal conditional is you need to prove that whenever you're in the domain and the hypothesis is true, the conclusion must follow. That's it. Whenever you're in the domain and the hypothesis is true, the conclusion must follow. So we start off by just having A, B, and C be any old particular, arbitrary but particular elements that are in our domain and satisfy the hypothesis. The important part is that they're arbitrary but particular, which again means that they're just like we're picking some out, but we can't assume they have any properties that not everything in the domain has. So let A, B, and C be arbitrary but particular integers such that A divides B and B divides C. So this is how you start every direct method proof, right? Just let these things be in your domain such that they satisfy the beginning. And remember, you might say like, well, how do you know A, B, and C are actually in a domain and do this? Well, you're just defining them to be that way because we don't care about anything that's not in the domain and doesn't satisfy the hypothesis because this statement is just a statement about things in the domain and have this hypothesis. So we're just gonna define A, B, and C to be those because we don't care about anything else. Right now, we'll care later. But not that I don't care, you know what I mean. You know what I mean. One thing at a time is important. We compartmentalize our caring in this class. And right now we're dealing with this compartment. So, yeah. So we have this right here. And then what can we do with these guys, right? Like this isn't necessarily that useful by itself, like labeling them like this, but what do these actually mean under the hood?
There exists like in a, right, we just use the definition of divides, right? There exists an A such that there's a K, there exists a K such that A times K equals B, where K is in the integers.
Because A divides B, what that means is B is an integer multiple of A, right? So there must exist some integer K, there must exist some K in the integers, such that B equals AK. I'll say similarly, since B divides C, there's a K and Z such that C equals BK. Now I made a mistake here on purpose. What's wrong with what I just wrote?
You should probably not have K for both A and, well, like B equals AK and C equals BK. Like
Exactly.
They can't be the same particular K.
I very much enjoy your humbleness, Alex. But no need to say probably. You're totally right. You know you're right, right? Yeah. The problem is here we use K to mean two different things, and that's a big no. Never use variables. Use the same variable, I should say. To represent two different things. Right? This is important. This is huge. I'm going to triple circle this. Please don't do this. Right? This leads to a ton of errors. This is a big common source of errors. A lot of people do this because, like, like use the same variables over and over again. We use similar letters, but make sure that every time you use different things, use different variables. So here I should really say, like, there is, I'll call it T or something like that, and Z such that C equals BT. Because here, K represents the integer multiple you need to multiply A by to get B. T represents the integer multiple you need to multiply B by to get C. These represent two very different concepts. Nowhere from our domain and our hypothesis does it specify that like A to B equals B to C, that K and T should be the same thing. Nowhere does it specify that, so we need to name them different things. Now, could K and T be the same depending on your A, B, and C? Yeah.
Absolutely.
It could be the same, right? For example, if A equaled 3, B equaled 6, and C equals 12, right? Your K here would be 2 to go to 3 to 6. Your 6 would be 2 to go to 6 to 12 as a multiplier, right? But the point is, even though they could be the same, they're not always going to be the same. So that's the whole thing about arbitrary but particular. These are arbitrary in the sense that we can't assume K and T are the same because we don't know they are based on for any old A, B, and C. And if they do happen to be the same, that's fine. It's okay if sometimes K would be the same thing as T. That's okay. So, to make that mistake, don't be me, right? I made this mistake right now, so you don't have to. Am I a martyr? Stop. Come on. But anyway, so we know that B equals AK and C equals BT. And then we have everything we need, right? We can just say thus. So we kind of work backwards here, right? We eventually want to get C as a multiple of A because we're trying to prove A divides C. So we want to get C as a multiple of A. So we're going to start with C and try to write it as something times A. So thus C equals AK by definition. By definition. And then AK, I'm sorry, sorry, B equals AK. C equals BT. By definition. But then B equals AK. This is what we call substitution because we're substituting AK for B. There we go. And substitution you do with things that are equal, unlike like a sub-teacher, because no substitute teacher could be as great as me at discrete math. Oh, but anyway, yeah, so C equals BT, B equals AK, so you can substitute that there. And then we can do this little parentheses trick, right? AK times T is the same thing as A times KT. And this is by what's called associativity. And associativity, for those people that either never saw it or forgot it, that just means that like X times Y times Z always equals X times Y times Z. That's just, and it works with plus too. Plus is also associative. S plus Y plus Z is the same thing as X plus Y plus Z. Yeah. That's very important. And then once we have that, that's kind of all we need. So now we've written C as A times KT, meaning that we've proven that C will divide, or A will divide C if what? We need one thing. We need to prove one last thing.
KT is in the integers
KT is an
because
integer. Right?
they're closed under multiplication.
Because, for example, you could always make something look like this. Like, for example, 17 equals 2 times 8.5. But this doesn't mean that 17 is divisible by 2. The reason being 8.5 is not an integer. So we need to be very careful to make sure that this is in fact an integer. We don't trick ourselves. We want to play ourselves. Is the whole point. Yeah. So we have A times KT. So let's note, since K and T are in Z, by definition, right? Because when we defined K, we said it to be in Z. When we defined T, we said it's in Z. Since K and T are in Z by definition, KT is in Z since the integers are closed under multiplication. And that's one of those things we're allowed to assume. Therefore, KT, this thing multiplied by A, is in fact an integer. Therefore, C, which equals AKT, is divisible by A by definition of divisibility. Square. We're done. That wasn't that hard, right? Any questions here?
Are all so associativity and stuff, that's the same rules that are in logic. Do those same rules have the same names, and do they all crop up in math as well?
Excellent question. I'm going to erase this so we can write some new things. Excellent question, Herman. And the answer is yes, they crop up in math, but not by necessity. Associativity is just kind of like the name we give to things. So, and commutativity and things like that. So commutativity, what that means, commutativity, yep. What that means is that for some operation, A times B equals B operation C. And so.
Wait, what, Professor? Shouldn't it be B times A?
Oh, yeah, my bad. Thank you very much, yeah. So plus is commutative because A plus B equals B plus A for all A, B in the real numbers and in the complex numbers, anywhere we extend it to, really. This will come back probably. But anyway, yeah. So multiplication is also commutative. But for example, division isn't. Right? Because if we do, let's say we do 12 divided by 4 divided by 2. The order we do this in massively matters, right? This would technically be, if we go left to right like PIMDAS says to do, 12 divided by 4, this would be 3 divided by 2. And 3 divided by 2 is 1.5. But if we do 12 divided by 2 divided by 4, I know I had 3. I didn't even do that. I mean, actually, an easier way would just be that 6 divided by 2 equals 3. 2 divided by 6 equals 0.66666. So, that.
0.33333.
Oh my gosh. Thank you, Alex. Yes. All right. Yeah. So not the same thing. But division is also not. Division is not associative. And so what I mean by that is that's what that example was shown before. 12 divided by 4 divided by 2. The order you do these in very much matters. Because 12 divided by 4 and then divided by 2, that equals 3 divided by 2, which is 1.5. But 12 divided by 4 divided by 2, that is 12 divided by 2, which equals 6. So the point is, commutativity and associativity, they're just names that we give to operations that have certain nice properties. Some have them, some don't. It doesn't matter if you're in logic, math, whatever you're in. Cool. Divisions are counterexample to so many of these things. Does not work nicely, sadly. But also exponentiation. Another one. For example, 2 to the 3 does not equal 3 squared. So exponentiation is not commutative. It's a whole thing. But anyway, yeah, any questions on the theorem that I'm erasing now? Didn't think so. Nice, cool. Let's move on. Let's do another theorem. Yeah, let's do another theorem here. Actually, I call this a lemma. Lemmas are words for tiny theorems. We'll go over this more later. It doesn't really matter. This is just vocab. Theorems in math are big facts that you prove. They're big facts that have been proven to be true. If they're not proven, they're called a conjecture. And conjecture is just, I think this is true. I'm conjecturing that's true, right? So theorems are proven things, and they're usually big and important. Lemmas are tiny little proofs that help us solve the big proof. So lemmas usually normally do before theorems, and then propositions or corollaries are things that happen after a theorem that you directly use a theorem to do. So like once you do a big theorem and then it's like, oh, the next thing's obvious, that next thing you call like a corollary, something like that. Anyway, yeah, so let's do a tiny lemma. This tiny lemma is that for integers a and b, if a divides b, then a will also divide negative b. Yeah. And so the formal way to write this would be for all a and z, and for all b and z, a divides b implies a divides minus b. Now this is the direct translation of this, but I'm actually, sadly for notes, going to change this to say a divides b if and only if a divides negative b. This actually goes both ways. So, and I think we can kind of see why. right? Like our side would be, I mean, think about it, right? Like 10 divides 20, and 10 also divides negative 20. Why does it divide 20? Because 2 times 10 equals 20. Why does it divide negative 20? Because negative 2 times 10 equals negative 20. You just make the multiplier negative, and you get the proof for free. Makes sense, right?
Professor, quick question.
Yeah.
It's similar to the concept or exactly the same as the biconditionals?
Oh, this is a biconditional.
Yeah. So the one you showed was just to prove like how it works both ways.
Wait, are you talking about the 2 and the 20 and the 10 thing?
Yeah, just to say that doesn't matter if it's a positive or negative, it's under Z, which is integers, because they have both positive and negatives.
Yeah. Positive, negative, exactly. And my little example just kind of show how it works. But you're right. We're going to prove it both directions. The fact that you can make the multiplier negative, like make 2 negative, to get that 10 divides negative 20 is important. But also, if you started with 10 divides negative 20, the multiplier is negative 2. That's because negative 2 times 10 equals negative 20. But then if you make negative 2 negative, you get that 2 times 10 equals 20. So 10 divides 20. So yeah, it goes both ways. That's what we're going to show right now. Proof. Yeah. So how do we start a proof?
Let like A and
We have to
B.
generalize.
There we go. Generalize. That's a good way to say it, right? Yeah, exactly. Let A and B, let A and B be arbitrary but particular elements of Z such that A divides B. And by the way, I forgot something. I got so excited about the arbitrary particular thing. Because this is a biconditional, remember we have to have 2 separate proofs. One proving it goes this way, one proving it goes that way. So I'm going to prove this way first. So you put a little thing there in parentheses, like this you should write in your homework and stuff. A little thing there in parentheses, and lets everyone know you're proving the first direction right now. You can put the second one first if you want, but then you just got to put the second direction, like the left arrow, that way. Yeah. So let A and B be arbitrary but particular elements of Z such that A divides B. I assume A divides B because I'm in this direction. I'm assuming this and proving this. So then, by definition, there is a K and Z such that the B equals AK. As always, that's what divides mean. It means there's an integer multiple. B is an integer multiple of A, but the integer is K in this case. And then we're going to do exactly what we did in the 1020 example. All right? Note so now we're going to try to show that negative B, negative B is a multiple of A, right? Because that's what it means for A to divide negative B. That's what we want to get to. So I'm going to start with negative B and try to write it as a multiple of A. So thus, negative B, which really means negative 1 times B, by definition, is going to equal negative 1 times AK. In this, we're substituting B for AK, or AK for B. So this is by substitution. And then by associativity here, right? Or actually by commutativity and associativity, this is going to equal A times -1 times K. By commutativity and associativity. And that's all we need, right? So then note that since -1 and K are in Z, by definition, and the integers are closed under multiplication, because we know those two things, -1 times K is in Z. Therefore, I like to end proofs with therefore. It feels exciting to me. Therefore, or ergo is a good word. But anyway, therefore, negative B, which equals A times -1K is divisible by A by definition of divisibility. Divisibility. Oh, we've got this important part. Ugh. The sweet release. There we go. I would have felt, that would have been a bottle up all day. I would have felt so weird. Any questions on that? Good. Yes, this is nice and simple. And by the way, this is the exact same way you'd prove that it's actually going to turn out that A divides B will imply A divides B times C. That's a conversation for a different day. Mainly because we're running out of time today, not because you guys couldn't do it today. So let's have a theorem. It's the same theorem we went over last time, and that is for integers A, B, and C, if A divides B and A divides C, then A will divide B plus C. And we went over this last time. I'll just do an example real quick of showing how that works. Let's say, yeah. For example, 3 divides 6, and 3 divides 6, and 3 divides 15. And so we're going to get that 3 divides 6 plus 15, which is 21. But before we do that, kind of a way we can see that is that if you have 1, 2, 3, 4, 5, 6, like that, notice 3 does in fact divide 6. And same thing here, if you have 15, 13. If you have 15, 3 also divides 15. And then, since 3 divides 6 and 3 divides 15, clearly, when you smush them together, right, One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, that's all we need. Clearly, when you smush them together, right? Here, 1, 2, 3, 4, 5, 6. Here's the 6. Here's the 15. And then clearly, we could just divide it up in the same place. Right? And 3 would divide the sum. The idea being if 3 goes into 6 evenly and 3 goes into 15 evenly, well, then it's going to go into 6 plus 15 evenly. Just smush them together. I think that makes sense. That's the idea behind this proof. Thus, 3 divides 6 plus 15. But that's a proof for homework. That's just theorem that we're going to use right now.
Quick question.
Yeah.
Can we use like diagrams for our proofs?
No.
Oh, okay.
That's why I drew that with green, because that's an aside.
I see.
It's kind of like a way to think about it. You can still use diagrams to organize your thinking and to guide you in your proof. We need these actual symbols for proofs. The reason being that things get messy with geometry. So even most geometric proofs today have been kind of algebratized, because the big reason really is because, for example, actually, remind me about this after class. Remind me about this in 5 minutes. I'd love to talk about it. But first, let's just do this part real quick. And so this part real quick is, yeah, so now let's finally finish that proof from last class. So let's recall our claim was that for any, and Alex is totally right, I should say positive, for any positive 4-digit number n, 3 divides n if and only if 3 divides the sum of the digits of n. That's what we're trying to do. And remember, like for example, 3 divides 57. Since 57 equals 3 times 19, right? And also notice that 3 divides 5 plus 7, which equals 12. That's just an example. That shows there's some merit to this. 3 divides 57 and also divides the sum of the digits. Because 3 times 4 equals 12. That's why that works. But yeah. So that was what we had right there. And then to do this, we defined a set S to equal the set of 4-digit numbers. I'll say positive. Which we can more formally write as a 4-digit number is any number that has 4 digits, right? So any number that equals 10 cubed, or A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 plus A0 times 10 to the 0, such that A3, A2, A1, and A0 are all in the set 0 to 9. So all these come from 0 to 9 because that's how digits work, right? Any digit in a number is between 0 and 9. Whole numbers are between 0 and 9. Let's just set S. And so the formal way to write this claim is for all n in z positive, that's just going to be the positive integers, 3 divides n if and only if there exists, actually I'll just say s, there you go, for all n in s, 3 divides n if and only if there exists A3, A2, A1, A0, and 0, 9, such that n equals 10 cubed A3 plus 10 squared A2 plus 10 to the 1 A1 plus 10 to the 0 A0. That happens. And 3 divides A3 plus A2 plus A1 plus A0. All this is saying is that 3 divides n if and only if 3 divides the sum of the digits. This part's just telling you how to write in as like base 10, basically. All right, so our proof that way we did last time. Done. This way, we'll do right now. So now, instead of starting with the, so now last time we proved this direction, which means last time we proved that if 3 divides n, 3 will divide the sum of the digits. But nowhere in that proof do we really find out that if 3 divides the sum of the digits, 3 must divide n. So now I want to go this way. So that not only does 3, if 3 divides n, 3 divides the sum of the digits, but also if 3 ever divides the sum of the digits, 3 will divide n. Does that kind of make sense, that distinction? Cool. That shows that these two things are equivalent, basically. They happen at the same times. So now we're going to start from this way. So this is going to be a direct proof. So let n be an S such that there exists A3, A2, A1, A0, and 0 to 9 with n equal to A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 to the 1 plus A0. All right, we have all that. Yeah. Oh, sorry. And 3 divides A3 plus A2 plus A1 plus A0. So because we're proving this direction, right, the first thing we do is just let n be an arbitrary element, arbitrary but particular element in S, where all this is satisfied. Where n can be written this way, which everything in S can, and 3 divides n. Or 3 divides the sum of the digits. That's the key. 3 divides this right here. So I want to prove that 3 must divide n. So what do? Well, we do the same clever thing we did last time, where we can actually use this to rewrite in a way that's more useful. So let's note that n equals A3 times 10 cubed plus A2 times 10 squared plus A1 times 10 to the 1 plus A0. By definition. But then 10 cubed is actually 1,000. 10 squared is actually 100. 10 to the 1 is 1. And we just have A0 here. And this is by evaluation, I'll say. Just doing 10 cubed and doing 10 squared and doing 10 and all that. Then remember the trick was 1,000 equals 999 plus 1. And 100 is 99 plus 1. And 10 is 9 plus 1. So for each of our digits here, and this is by addition, thus each of our digits here, if we distribute this out, we'll retrieve A2 times 1, A1 times 1, A3 times 1. We'll get all of our digits with some stuff left over. The stuff left over being, this is going to be 999 times A3 plus A3 plus 99 times A2 plus A2 plus 9 times A1 plus A1 plus A0. This is by distribution. And this is going to equal, if we group it together, if we group kind of this extra bit together, 999 A3 plus 99 A2 plus 9 A1, and then we have the A3 plus A2 plus A1 plus A0. So the key is by looking at it in this way, we will recover the sum of our digits right here. And now we're so close to being done. So everyone remember this, because I'm going to erase to get more room. Actually, yeah. All right. So we're still going with the proof. So pretend like I just paged down. So we have that n equal ... It was 999 999 A3 plus 99 A2 plus 9 A1 plus A3 plus A2 plus A1 plus A0, which equals, this right here is a multiple of 3, right? Because 999 is multiple of 3, 99 is, and 9 is. This 3 times 333 A3 plus 33 A2 plus 3A1. And this is by factoring. So note, 999, this is 3 times something. So this is this right here is divisible by 3. And this, by definition, is divisible by 3. So n equals something divisible by 3 plus something divisible by 3, which by our theorem means it'll be divisible by 3. That's the brilliant part here, right? The brilliant part is we rewrote n in this way as something plus the sum of the integers, or the sum of the digits, and that something happens to be divisible by 3. So that's why all this works out. So note, since 3 is an integer, 3 divides 999 A3 plus 999 A2 plus 9A1 by definition. Therefore, by theorem, since 3 divides 999 A3 plus 99 A2 plus 9A1, and 3 divides A3 plus A2 plus A1 plus A0, that was by the assumption of the problem, since we're starting here and trying to get here. 3 divides in, which equals 999, A3 plus 99, A2 plus 9A1 plus A3 plus A2 plus A1 plus A0. Done. All right. Sorry for going over. Class is over. My bad. This proof always takes longer than I think it will. But the reason I want to show you guys this proof, even though it's a little more complicated, I think it's probably a little above maybe the scope of this class. Like I wouldn't probably ask them this hard on a homework just straight up or on a test just straight up. But it shows you that just with the information we have, we can prove some kind of powerful things. And this is not obvious. I mean, like you could do some examples in your head and convince yourself it worked, but it's not obvious that this works for any single multiple of 3, but it does. So now, if you didn't know this rule before, right, if anyone gives you any number, you can be like a magician. If anyone gives you any number, right, you can very quickly tell them if it's divisible by 3, and you can tell them why. Although people don't usually like the why. They get mad at you. But anyway, yeah, any questions? Well, that's class. This is all leading up to this. The point is, this is a cool rule, but we don't really care with the rule. Like, this will probably never come up in this class again. We have to apply this. It's the idea behind the rule. The idea behind, oh, we can rewrite in a special way like this, and we can use what we know. We use this theorem down here, and it all works together. And this is a cool example of biconditional where it goes both ways, where 3 divides in, you know, it divides the sum of the digits. If 3 divides the sum of the digits, you know, it divides in. I'm talking in circles. I should quit. Okay, I'm stopping recording.